Okay. Şimdi ne yaptık? En son P noktasını bu şekilde yazdık. Let's see. So, let me switch the board. Well, similarly, of course, f of p is f of p dot f of u1, f of u1 plus f of p dot f of u2. No, I don't have this. F of u2 plus f of p dot product f of u3 times f of u3, because this is an orthonormal basis also, right? Is an orthonormal basis also. Right? For any orthonormal basis and a vector, I take this vector. This vector is just, it can be written in this orthonormal basis, where the coefficients of these vectors are just the inner products of that vector with the basis elements. Okay. However, we know the following. F of on the other hand, since F preserves the inner product, we have this f of p dot product f of ui is just p dot ui, right? F preserves the inner product, so I have this. Hence, we have the following. F of p, which is equal to this expression, but instead of this, I can write just p dot u1. P dot u1, and then here I have f of u1, right? Instead of f of p times f of u1, I write p dot u1, then f of p1 plus f p dot u2 times f of u2 plus p dot u3 times f of u3. I have this. Okay. We are almost there. Okay. Now, finally, we have this f of p plus q. Now, I can apply the same formula to f of p plus q. So here I will have just P plus Q instead of P. So this is just P plus Q dot U1 times F of U1 plus F plus Q dot U2 F of U2 plus F plus Q dot U3 F of U3. However, dot product is linear. Instead of this, I can just write F dot U1 plus, not F, P dot U1 plus Q dot U1, F of U1 plus P dot U1 plus Q dot, not U1, U2, F of U2, and P dot U3 plus Q dot U3, F of U3. However, I can arrange these as follows. So here you see I have P dot U1, P dot U2, P dot U3 multiplied with F of U1, F of U2, F of U3. So let me just write that down. P dot U1 times F of P1 plus P dot, not P1, U1, P dot U2 F of U2 plus P dot U3 F of U3 plus I have the same thing this time with the vector Q. Q dot U1 F of Q1 U1 Q dot U2 F of U2 plus Q dot U3 F of U3. Well, the first three terms, these three terms is just this expression, right? So it is just F of P. So the first three terms adds up to F of P, and the remaining three terms adds up to F of Q. So what we have seen is then, hence we have this. F of P plus Q is F of P plus F of Q. Okay, this is half of linearity. We have to also show that constants goes out, right? Let's also see that. Okay. Moreover, for any real number.
Pardon hocam.
Evet.
Tahta geride kaldı.
Evet, haklısın. Okay. Moreover, for any real number lambda, we have F of lambda times P. What is this? Well, I can write this as follows. Again, this is just lambda P dot U1 F of U1, right? Plus lambda P dot U2 F of U2 plus lambda P times U3 F of U3, right? F satisfies this equality, and here I can just take this lambda out, right? Because it is lambda times a vector inner product with U1. inner product is linear in both components, in both P first component and the second component. Therefore, I can take this lambda out. So this is just lambda times inner product of P and U1, f of U1, plus lambda times P dot U2, f of U2, plus lambda times P dot U3, f of U3. But you see, lambda term is common term, and if I take everything in the lambda parentheses, what I get is just f of P, right? So this means you can take this lambda outside. This finishes the proof of the proof. This finishes the proof of the claim. Claim that f is linear. So we are done. F is a linear transformation, and we have also shown that f is orthogonal, right? It preserves the inner product. Therefore, it's an orthogonal transformation. Sorusu olan var mı? Okay, so theorem is the following. If f is an isometry of R3, then there is a unique translation and a unique orthogonal transformation translation'a da isim verelim. Buna T diyelim. Sorry. Buna da C demiş. So that f is T composition C. So any isometry is a composition of T, a translation, and an orthogonal transformation, and T and C are unique in this sense, okay? No, they don't commute, but you can also write it that way also. That's but another representation of the isometry. But if you want to write it first as a orthogonal map and then a translation, then it should be like this, okay? And the proof is really simple. Actually, one of your friends suggested the idea last hour. So let f of 0 is equal to a. We have seen that if the image of 0 is 0, then it's already an orthogonal transformation. But in general, image of 0 need not to be 0. It can be any point in the plane, in the space. So let's say it is f of a. Let t be the transformation, translation along the vector a. So T of P is equal to P plus A for all P in R3. Okay. But then consider the following. I know that T is an isometry, F is an isometry. Inverse of an isometry is another isometry. So we have this. Then T inverse composition F is an isometry. Because T is an isometry, its inverse is also isometry. In fact, both of them are translations. One of them is translating along A, the other one is translating along minus A, right? So this is also an isometry. All right. But note that T inverse composition F of A is what? Sorry, 0. This is just T inverse of F of 0. Well, F of 0 is just A, and T inverse of A is what? T is translation along the vector A. T inverse is translation along the vector minus A. So this is just A minus A, which is 0. Therefore, T inverse composition F is an isometry, and it fixes the origin. But we have seen that any isometry that fixes the origin, if it doesn't move the origin, then it has to be an orthogonal transformation. So that's the next thing we will write down. Okay. Şöyle koyayım da. Hence, by the previous lemma,
Hocam yine pardon tahta.
I am sorry, I just keep forgetting. Hence, by the previous lemma, T inverse composition F must be an orthogonal transformation. Say C. Okay. Then what is F? F is just T composition. T composition. T inverse composition F. I can write it this way. T composition, T inverse is just identity, but this is just T, and then this is just C. So F is written as T composition C. Okay. There is also the statement about uniqueness, right? Unique translation and unique orthogonal transformation. Let's also talk about that. For uniqueness part, let this F is equal to T composition C and T bar composition C bar for some other translation T bar and orthogonal transformation C bar. What I have to show is the following. I have to show that T is equal to T bar and C is equal to C bar. Okay? Must show T is equal to T bar and C is equal to C bar. Let's see. Okay. But this equality, T composition C is equal to T bar composition C bar, they're all one-to-one and onto maps, right? They're isometries. They have inverses. So I can just move them around. So T composition C is equal to T bar composition C bar implies the following. T inverse composition T is equal to C bar composition C inverse. So I put T bar inverse to both sides. Here I get identity. Here I will have T bar inverse composition T and put C inverse to this side. C inverse times C is identity. And here I will have C bar composition C inverse. But then we have what? These are both translations. So this is a translation, right? Composition of two translations, right? T is a translation, T bar is a translation, its inverse is a translation, and then I have composition of two translations. This is a translation. And if you compute this translation at the vector 0, you get what? It should be C bar, C inverse of 0. But these are orthogonal maps. They are linear maps, right? They are matrix multiplication. You multiply the corresponding matrix for this with 0, you get 0. And then corresponding matrix for this orthogonal transformation times 0 is also 0. So this side is just 0. Okay? Because this side is just matrix multiplication. So this means what? This is a translation, but it keeps 0. Well, the only translation that keeps 0 is the 0 translation, right? Because a translation should be what? It should be 0 plus something, right? Any translation is given like this. You just add a vector to your point of application. But 0 plus a is equal to 0 implies a is 0. So that is the translation along the 0 vector. Well, this means this is just identity map, right? It doesn't move anything. But this means, sorry, T bar. T bar inverse composition, T is identity. This implies T and T bar are the same. Well, if they are the same, then, right, this is just identity. This implies C bar composition C inverse is T bar inverse composition T. But since they are the same, yanlış yaptım. This is T bar inverse. This means T and T bar are the same. Değil mi? Yani bu aynı zamanda t'nin inverse'üymüş. T'nin inverse olduğuna göre t bar t'ye eşit. But this is identity. So C bar and C inverse gives us identity. This means C equals C bar. So what we have seen is then C equals C bar and T equals T bar, and this finishes the proof. Tamam mı? Okay. In the remaining time, I'll talk about orientation. Yeah, the same proof. The same proof. So your friend suggests the following. Does the same thing hold for Rn? It does. You can generalize all the definitions and statements we have used so far to higher dimensions. Everything works. We may define the isometry the same way, translation and orthogonal transformation same way, and the same conclusion will hold, saying that any isometry of Rn with the Euclidean inner product, equipped with the Euclidean inner product, is a composition of a translation and then orthogonal transformation. So the same result holds for Rn equipped with the Euclidean all right, I forgot. So the same result holds for Rn once it is equipped with the Euclidean inner product. Okay, you may just go over the proof, and you will see that there is no importance being in the 3 dimensions. Okay, the same definitions and results will hold for any Rn. Okay. Yeah. What was my okay. I will skip 3.2 and jump into 3.3 orientation. Okay. From high school, this right-hand rule, right? Used in physics. So that's just a mathematical, formalization of that thing. A frame, I mean an orthonormal basis, okay? A frame E1, E2, E3 at a point is called positively oriented. oriented if E1 cross E2 is equal to E3. So here I am at a point P, let's say, and we have a frame. Okay, E1, E2, and E3. Okay. Yeah. So it is called positively oriented if E1 cross product E2 is equal to E3. We know from the properties of cross product that if you have two vectors, their cross product, unless it is 0, is a vector in which is perpendicular to both of them. In our case, they are all unit vectors, orthonormal vectors. So cross product of two of them will be either that vector or it's negative, right? Because it will be perpendicular to both E1 and E2, and E3 is perpendicular to both E1 and E2. Therefore, this cross product is either, for any orthonormal frame, this product is either E3 or minus E3. I will call this basis positively oriented if E1 cross E2 is E3. Okay. Example. So E1 okay, 1 0 0, E2 0 1 0, and E3 0 0 1 is positively oriented. However, I can write another inner product. I can write another orthonormal frame, which is not positively oriented, namely this one. However, this one, I take V1, okay, let's say F1, 0 1 0, F2, 1 0 0, and F3, 0 0 1 is not positively oriented. Since F1 cross F2 is equal to, cross product of these two is not F3, but it is minus F3. Okay. If you switch the order of two of them, you get minus sign. So this basis is not positively oriented. It doesn't satisfy the right hand rule. Okay, here is a remark. Sorry? Yeah. It's all about order, actually. Okay. If you are given a basis, if it is negatively oriented, just switch the order of two vectors. It will be positively oriented. Okay, because that I will show you in a minute. Switching order of two vectors is switching rows of a matrix, and orientation is determined by the determinant. So when you switch the order of two vectors, place of two vectors, then determinant picks up a minus sign. So if it is positive, it becomes negative. If it is negative, it becomes positive. So that's the next statement. Note that if E1, E2, E3 is an orthonormal frame, well, if it's a frame, frame means already orthonormal, sorry. Yani orthonormal frame demeye gerek yok. Zaten frame deyince orthonormal alacağız. Is an orthonormal is a frame, then E1 cross E2 dot product with E3 is what? This is just it is, this thing is either E3 or minus E3. I know that, right? Because they're all orthogonal to each other. The cross product of these two vectors, right? I have E1 here, E2 here. The cross product of these two is a vector perpendicular to both of them. So it is this one, in our case, E1 cross E2. And E3 is either this one or it's negative. I don't know which one. So E3 can be this one or the other one. So this is either, so this is plus or minus E3 dot E3. And this is just plus or minus 1. And it is plus 1 if and only if this is just E3. If it is minus 1, it means that E1 cross E2 is just minus E3. So, and it is plus 1 if and only if, E1, E2, E3 is positively oriented. So this is a quick way of checking whether a frame is positively oriented or not. Just write down this product, cross product of the two vectors, dot product with the third one. Okay, if it is plus 1, then it is positively oriented. Otherwise, it is negatively oriented. And from linear algebra, we know that we can also write it this way. How? Okay, let me switch the board first. All right. Moreover, E1 cross E2 dot product with E3 is what? This is just, you write here E3 and then E1 and E2, right? It is the determinant of this matrix. Neden? How would you compute the cross product? You write here IJK and the vectors E1 here and E2 here. Instead of IJK, I have the vector E3, right? You take, okay, you can just, see this in a minute. So it is just the determinant of this matrix. And determinant of this matrix is the same as determinant of this one. I can switch this to, that will change the sign of the determinant, but then, so I write E3, no, E1, E3, E2, that picks up a minus sign, and then I switch this to, I get another minus sign, so it becomes plus. Therefore, this is equal to this gadget. E1 cross E2 dot E3 is equal to this one. So this means what? Hence, E1, E2, E3 is positively oriented. If and only if the determinant of the matrix E1, E2, E3 is +1. Okay. Well, an isometry will map an orthonormal frame to another orthonormal frame, right? We know that because isometries preserves inner products. They preserve length, therefore it's the inner product. So an isometry maps an orthonormal frame to another orthonormal frame. But whether it keeps the orientation or not is another question, right? Your original frame could be positively oriented, but its image under a sorry, isometry may not be positively oriented. Okay. Okay. Preserves the orientation. Preserves the orientation means it maps positively oriented frame to a positively oriented frame. In other words, it maps positively oriented frames to positively oriented frames. Is called orientation preserving. Biraz garip bir şey oldu ama. Okay. Şöyle yapayım. Bunu statement'a çevireyim. Let me if and only if its orthogonal part has positive determinant. So take any isometry. Any isometry has the following form. It is a translation and an orthonormal transformation. If I have, let's say, a point here and a frame at this point, let's say E1, E2, E3, a positive frame, positively oriented frame. F of this will be what? When you apply orthogonal transformation, it will rotate this vectors, right? O zamanım doldu mu? Okay, let me stop here. I'll continue next time. Sorry.